Hi guys, welcome back to Data Every Day. Today we're looking at a data set of super shops in the USA. So we have it's different transactions from different stores, and we're going to try to predict the profit gained from a given transaction based on the rest of the features. So it looks like we have the sales and the quantity purchased, and then the type of product. And then we try to predict how much profit the shop gets based on those features. So let's hop into the notebook. We're going to use NumPy and Pandas for working with the data. For visualization, I'll just do a chart at the end. We'll use pyplot and seaborn. And then for pre-processing, we'll use the train test split function and standard scaler from sklearn. We'll build a model with TensorFlow, and we'll use the R-squared score from sklearn to evaluate the performance. So let's go ahead and import all of that and load in the data using pandas.read.csv. We can grab the file path to the CSV file up here. I'm just going to go ahead and paste that in. We can take a look. So it's a pretty nice, clean data set. If we take a look at data.info, we should be able to see there are actually no missing values in this data, which makes our lives easier. This is going to be a regression task. So we're predicting profit. This can be negative or positive. So it's a continuous scale regression task. So let's start pre-processing. Really, the bulk of the pre-processing is going to come from encoding the categorical features, since we have so many. We have 8 object columns. So pre-process inputs is going to take in a data frame as a function of making. It's going to copy over the data frame, and for now all it will do is return the data frame. And let's get back the processed version of the data and store it in X, passing in data to our function to get the result. X right now is just a copy, but this is the copy that we'll perform our pre-processing on. So the first thing we should do would be to identify a few things about the data. Well, the first one, which we already sort of did, is just to make sure we have no missing values. And yeah, we have 0 missing values in every column, so we don't have to worry about that. Next thing to do is see what is the cardinality of our categorical columns. So by cardinality, I mean how many unique values does each categorical column have, because that will affect how we want to encode them. So we're going to create a dictionary that maps the column name to the number of unique values in the column. And we get that by taking X subcolumn, taking the .unique of it to return a list of unique values, and then taking the length of that list. And we can do this for every column in x.columns. So these aren't all the categoricals, these are actually just all the columns, but since we're only working with 13, this is okay. So we should note that there are a few numerics. In fact, sales, quantity, discount, and profit are the only numeric variables here. So we just sort of exclude these from what we're looking at. We don't need to look at those. So of our categoricals, we want to see what is the cardinality like. So these are actually all reasonable cardinalities. The reason I say reasonable is if you have a really high cardinality column, it can be very difficult to encode properly. If it's a nominal feature, then you'd have to send each unique value to its own column to one-hot encode it. And that, if you have 10,000 unique values, that means 10,000 new columns, can really slow down the performance of the model and can lead to overfitting. So we are actually working with a nice set of cardinalities here. We have a few in the mid-hundreds, but that's okay. We're using a neural network today. Neural networks are particularly good at dealing with high cardinality data. Okay, so I think most of these are going to be one-hot encoded. And I should point out that postal code, even though is actually integer column, this is categorical. These are not meant to be interpreted as a continuous range. So we're going to want to one-hot encode that as well. And I don't see any columns here that are ordinal. The only one you might consider as an ordinal feature would be the ship mode. If we look at the unique values in ship mode, you can see you could sort of rank these. However, encoding it as an ordinal feature may present some issues because we don't know how to rank them. Like, would we send second class to 0, first standard class to 1, first class to 2, same day to 3, or in the other direction? where is this spacing of the integers come from? We're just sort of making it up and it doesn't have a basis in reality. So we shouldn't do that. Now, in practice, I would always try out various types of encoding to see which gives you the best results. But from a theoretical perspective, it makes probably more sense to nominal encode or one-hot encode this column than it does to ordinal encode. And if you're not sure what ordinal encoding is, it's just sending each value to its own integer. Okay, so I think we'll just one-hot encode all of them. So let's do that. Oh, actually, we should point out the country column has only one value in it. When you have a column with only one value, the column is useless. So the reason there's no way to draw distinctions between training examples using the column. So we just drop it. Let's drop country, drop single value column. df equals df.drop country from axis 1, which is the column axis. Alright, so country is gone. The remaining columns are all have multiple values. We also don't have any binary features. Binary feature is a categorical with only 2 values, and we don't have those. So we know these are all candidates for one-hot encoding. So let's go ahead and, I guess over here, we'll just grab the names, all these columns, and we're going to one-hot encode them. One-hot encode nominal feature columns. So what I'll do is loop through this list. So for column in, and I'll put these in a list. Let me just clean it up a little. Alright. For each of these columns, what we're going to do is create some dummy columns. So we're going to use Pandas.Getdummies to do this. This allows us to pass in some value. Let's use the city column, for example. And it will send each unique city value to its own column. And a 1 in a given location. I actually can't see with this one. Let's use state instead. So a 1 in a given location represents the original value of an example. So you can see how this is a good encoding for categoricals, nominal features. You can also include a prefix in this function. Let's call it state. And that will just put the word at the beginning of each column name so that you know where these columns are originally coming from. So up here, for each of these columns, we're going to create some dummies using Pandas.Getdummies for df subcolumn for any column. And the prefix will just be the same as the column name. Alright, then we're going to take the dummy columns and we're going to add them on to the side of our data frame. So for this we'll use pandas.concat, concatenating the original df and the new dummies side by side, so axis 1. Then once they're concatenated, we can drop the original column from which we created the dummies. And that should do it. We run this now, take a look at x. Okay, we now have 1,200 columns, and you can see all of these are one-hot columns. So we actually only have 4 non-categorical columns here. The majority of our data is now encoded as, is just an encoded form of the categoricals. Alright, you can see the ones in there corresponding to the original values. So, I think the last thing we should do is split and scale the data. I don't see anything else to do here. So let's split the data. Split df into x and y. Y is going to be the column we're trying to predict. So that's going to be the profit column. And then x is all the rest of the data, which will be our feature data. So we're dropping profit from axis 1, storing it in x. Then we'll do our train test split. So we want to split both ways, vertically and horizontally. You could think of this as the vertical split, and then this is the horizontal split. So we want to send 70% of the data to the train set, and the other 30% to the test set. And that 70% number is arbitrarily chosen. Some people like to use 80 as well, even 90. 70 seems to work well for me. You want to strike a balance between having enough data in your train set to have the model learn, and having enough data in your test set to get accurate reading of your results. So xtrain, xtest, ytrain, and ytest are going to be the new sets of data that we're going to get using the train test split function from sklearn. We're going to pass in x and y, specify the train size we'd like I said 70%, so 0.7. Keep shuffle equals true on, so that will shuffle the data before it makes the split, which makes our lives easier so we don't have to do it. And then it will include a random state so that the shuffle is always made in the same way. And we can reproduce the results of the notebook. So let's return these 4 values, get them back over here, and let's take a look at xtrain. So xtrain no longer has the profit column, and it's using only 70% of the original data. Ytrain should be just the profit column, and again 70% of the data. Alright, and the last thing to do would be to scale the data. So right now you can see most of our data takes on, most of the columns take on a range of 0 and 1, because most of them are one-hot columns. But some of them do not. Over here we have numbers going up into the hundreds and down into the negative hundreds. So what we want to do is scale the columns so that they all take the same range of values. One way to do this is using a min-max scaler, where you can compress the max of the column and the min of the column down into a given range, usually between 0 and 1. However, such an approach can often be not so great at handling outliers, because if there are outliers in the data, it will compress a lot of the information down into a very small range. So instead, one thing we can do is the standard scaling, which is standardizing the columns, doing a shift and scale to each column so that we set the mean and variance of a column. Usually this is done so it has a mean of 0 and a variance of 1. And we can do this with a standard scaler from sklearn. So scale x, and we'll create the scalar object here. And we're going to fit the scalar just to the train set, because we want to pretend we don't have access to the test set when we're doing the scaling, or when we're doing the pre-processing. And then we'll transform the train and test set using scalar.transform. So this actually returns a numpy array. If I run this now, you'll see xtrain is just a numpy array. It has been scaled, but we don't get to see it as a data frame anymore. So why don't we go and turn that back into a data frame afterwards. And let's keep the indices the same as they were before, and the column names the same as they were before. Sorry, this should be xtrain.index. Alright, and then we'll copy this over for the test set. Alright, and there we go. We have scaled data, so all the columns take on the same range of values. Using the standard scaler, most of the values will fall between -1 and 1 for a given column, but it's not hard capped at those values, just so long as the means are all the same and the variances are all the same. You can actually see that the means here are all very close to 0, and the variances are all very close to 1. So the scaling is complete. Now let's start training. So let's look at the shape of our input, xtrain.shape. For a given training example, we're getting 1246 inputs. So when we create our model here, the first input layer should be tf.keras.input, and the shape is going to be 1246. So we're inputting a vector of length 1246, and then those inputs are going to get fed through 2 hidden layers. So let's do tf.keras.layers.dense. We'll give them 128 neurons with a ReLU activation function, and pass in inputs to the first one, copy it over, and then pass x into the second one. In our output column will also be a dense layer. This is going to return a single value, which will be the predicted profit for a given example. The activation here is going to be linear, which is the same as saying no activation. So this one value that we return is uninhibited. It can take on any of the real numbers, and it's supposed to match up to these. So we're trying to predict profit. So hopefully the range of this will be constricted to the range of our ytrain. And we'll pass in x and then create our model. So tf.keras.model. The inputs of the model are given by inputs, and the outputs are given by outputs. I'm going to compile the model. The optimizer we'll use is Atom. The loss function will be MSE, mean squared error, since it's a regression task. And then we'll fit the model, store the results in history with model.fit. We're fitting on the train set, so x train, y train. Validation split, let's then set 20% of the training data for validation. And then we'll give it a batch size of 32. And we'll train for 100 epochs and use early stopping. So we'll use the tf.keras.callbacks.early stopping callback. This allows us to monitor a value, let's say validation loss. And when the validation loss starts increasing, or when it stops improving after 3 consecutive epochs, so our patience will be 3, then it'll automatically stop the training and restore the weights from the best epoch. So restore best weights equals true. Alright, we'll run that. There we go. It shouldn't be too long, it should be very quick. And you can see it already started to overfit after it looks like the second epoch. So the early stopping kicked in, restored the weights from epoch 2, since we had the lowest validation loss in that epoch. Now, let's get some results. So, okay, so basically, for a regression task, there are a few ways you can analyze the results. One way, which is a nice way, is to take the square root of the loss evaluated on the test set. And the reason the square root, if you're using mean squared error, this is, mean squared error is really a measure of how far off your predictions are from the real examples. But it's in the squared unit of the target column. So what I mean is, y-train looks like this. If we get some predictions using model.predict on next test, you can see we do have predictions for each example. Actually, we should look at y-test here. So these are our predictions, and these are the real examples. Now, the mean squared error is saying, on average, what is the squared difference between a real example and a prediction? Since it's in squared difference, in this case these are dollars, where the mean squared error is returned in the unit of squared dollars. So we can actually get the mean squared error using model.evaluate on the test set, passing in y-test to compare to. And so we have a mean squared error of 90,000. So on average, our squared error is 90,000. So what we can do is take the square root of this. Let's just include verbose equals 0 so we don't see that loading bar. We take the square root to get the average error in dollars instead of squared dollars. So you can think of this is called the root mean squared error, or RMSE. RMSE. And you can think of the RMSE as sort of a measure of how far off are you on average. So this is actually really useful for understanding the model, or how it's doing, because this kind of metric isn't reliant on it's useful whether or not you have other models to compare to, because it gives you a sense of how the model's doing from like an intuitive perspective. Based on the task, if you're looking at these profits, and you're looking at the kind of range we have, if we're off by $300 each time on average, then that's not so good. You can see we're dealing with pretty small numbers here. I mean, we do have 7,000. I can't make that assumption just by looking at these. But being off by $300 probably isn't great. And we can actually verify this even further, which we will. So what I'll do is print out the RMSE. So test set RMSE. And we'll display it to, I guess we'll display it to 2 decimal places since we're seeing this is supposed to be dollars. Formatting this with RMSE. Okay, so I forgot the F. Alright. I guess we could even put a $sign. This is because our average dollar error. Then what we'll do is get the R-squared score. So the R-squared score is a measure of how much better we're doing than the null model or baseline model. So the null model is what model you use when you don't have any feature data available. If we just had y-test and we had no x-test, what is the best guess we could make for a given example? It would be the mean of the labels. So the best thing we could do is predict this every time. Predict $30 regardless of what we're looking at. We have no input data. So what the R-squared score does is it checks how much better are your predictions than the null model. And it, on a scale of negative infinity to 1, where 1 means you have 0 error, you're doing you're doing perfectly. So you're doing 100% better than the null model. And negative infinity represents doing infinitely worse than the null model. So let's get the R-squared score. For that we need a set of predictions called ypred. So we'll get that with model.predict on xtest. And you'll notice down here if I run model.predict, it returns it as a two-dimensional array. So I'm just going to squeeze it down into one dimension with numpy.squeeze. And that's going to be our ypred. Then we'll get the R-squared score using the R2 score function from sklearn. We just pass in the true labels and the predictions. We'll call that R2. And we'll print it out. Test set R-squared score. So this will display to 5 decimal places, format with R2. Alright, last thing I want to do is print, I want to display a plot describing the predictions made against the actual target values. So we'll create a figure with a figure size, I think 10 by 10 is good here. I want it a square. And we'll use a Seaborn scatter plot to plot the predictions on the x-axis. So ypred is on x, and I want the real values, the actual values on the y. So we'll give it some bounds. So the limit on the x, since the predictions, what is the range of predictions? Let's see. So y-test, let's just look at y-test, and then dot min. Min is negative 6,000, max is positive 8,000. Can we describe this? Not sure if that works on a series. It does. Okay, so the standard deviation is about 320. The 25 percentile is 1. The 75 percentile is about 30. So it looks like most of the data is in the positive integers, or around the positive, small positive values. But I guess what we can do is put this on a scale of negative 1,000 to positive 1,000, which sounds reasonable to me. So negative 1,000 to positive 1,000, and we'll do the same for the y limits. Alright, then we'll give it some labels. So the x label will be the predicted values, and the y label will be the actual values. And then we'll give it a title, which is predicted versus actual values, and we'll show. Alright, so yeah, this is not so good, right? This is very informative. The R-squared score is telling us we're doing 12% better than the null model, which is not great. You can see here, so the actual values, if you look at the conditional distribution, well, the distribution of the actual values, you can see it's fairly well spread out, with the majority of them being here. This is just looking at the y-axis. If we look at our predictions, the distribution of our predictions are really confined to this small location. And it looks like the reason for this is probably because there's so much more data in the middle than there are on the edges. So our model is not so good at making these big predictions or really small predictions. It's most used to making predictions around this area, which line up with the most of the data and the actual values. Now, what we'd like to see here is a perfect line across the y equals x line, because that means that our predicted values match up perfectly with our actual values. But you can see we're actually doing not so well in that regard. Now if you think about the null model, that would be predicting the mean every time. So the mean was at 30, I think we saw it was 30. So if you could imagine just predicting 30 all the time, which would be like running a line up here, ours is about 12% better. And you can see it's just slightly better than predicting a straight line going down. It's like slightly slanted towards the y equals x line. So as our r-squared goes up and as our RMSE goes down, this plot will look more and more like a y equals x line. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.